Okay, I hope you're still feeling fresh for the final section for today's lecture in data science for energy system modeling. We want to talk a little bit more about optimization, or in general about electricity markets in an operational setting. So things that we don't discuss about yet today is how do we plan renewable systems, but we want to understand more how electricity markets work conceptually in energy systems, and how we use optimization models to represent electricity markets. Again, we're recording, and we'll put the recording on Zoom. So if you think back to the pandas tutorial in one of the first Python tutorials we had in this course, then we worked with this data set from power plant matching of power plant data in Europe. And kind of what we have as precondition here is that we have many different power plants in Europe, many consumers also in Europe that are all interconnected through the power grid. And the guiding question for this lecture would be, how do we actually decide which of these power plants produce at a given point in time? So if you look at an aggregate view and for a moment take a step back and only look at Germany and at a data set where we're actually looking at a state of 2022, when we had a lot less wind and solar than we have nowadays. But on the right, you can see some of the more up-to-date values, and you also don't have still a few nuclear power plants running in this system. If you look at the total capacity here, we're looking at about 200 gigawatts of total capacity compared to a peak electricity demand of 80 gigawatts. And part of that kind of mismatch in capacity is due to the wind and solar that is maybe not available at all the times, where you then need enough backup capacity or dispatchable capacity to fulfill the peak demand. And if you look at just the things that you have control over how and when to dispatch them, then you're roughly ending up in the order of magnitude of peak demand, maybe a little bit more, because you always have to think about scheduled maintenance or unplanned outages of conventional power plants as well. So this is kind of a very static view. We have kind of this bar basically changing with the weather conditions and also with the availability of conventional capacities. And that's the supply side. And on the demand side, we have over time varying demands, which must be met with the available generation capacity at any point in time. And of course, we're starting with a conceptual view, so we're neglecting all kinds of real-world complications, such as cross-border power flows between different market zones, demand flexibilities, and grid constraints. So we really just look at an isolated German system, perfect transmission in the system without any losses, and exogenously given demands. So if we do that, so one way to decide which power plants should be operating, well, you would probably agree we should start with the cheapest ones and then fill up the next cheapest ones until we meet the demand. And that is the concept of the merit order, where we just kind of take our generators, sort them by their marginal cost, and stack them onto each other. So we have here a certain volume of wind that can be generated at very low marginal cost, or almost zero marginal cost. And then we have, in this case, we don't have any CO2 pricing. So the brown coal in brown comes next as next lowest cost. We have nuclear somewhere in between. Between the technologies, we maybe have different smaller steps related to the efficiency of the power plants. So they can offer a highly efficient conversion, can offer electricity at a even lower marginal price. And then we have all the way up to gas in red and oil in black with very high marginal cost. So how do we decide which ones operate? Well, one intuitive way would be to say, okay, everything in this order until we meet the demand, which is represented here by the vertical line. And that is in principle how it goes in the electricity markets. And the price here would be set by the generator, kind of the highest cost generator that is still producing. And that price would be the compensation for the electricity produced by any of the other power plants as well. So also these wind power plants here that generate electricity at much lower marginal cost, they would get this price as a compensation for the electricity they produce. And this difference in the short-term view, it's a profit. In the long-term view, it is a profit that is used to finance the investment decisions building the wind plant itself. And this picture, it basically changes for every hour. We can have, oh, we can have 1 segment here midday with a bit lower demand. So you have the vertical line shifting to the left and a little bit more solar, which comes in at very low cost, a very low marginal cost, and that shifts then everything to the right so that actually none of the coal power plants in gray here, hard coal power plants, would be operating anymore. And the price, the clearing price, would also be lower because now the intersection point is here at the nuclear case, and here nuclear sets the price. In reality, it looks a bit more complicated. The supply side here is already quite well represented, but the demand side here is strongly simplified by just assuming a fixed value. In reality, we would have kind of the supply bits, or yeah, the supply curve of basically the merit order here in gray. And then we would have, instead of a vertical line, we would have a similarly shaped demand curve, which represents the willingness to pay for demand. So we have a couple of consumers that have a very high willingness to pay for the electricity, 4,000 euros per megawatt hour. And then we have a few consumers that have quite a low willingness to pay. In this example, actually even negative willingness to pay. So they're just willing to be paid to consume extra electricity. And similarly here, we would look at the intersection point, which would give us the market clearing price. And I think in this example, clearing price is quite low. We have 14.18 euros per megawatt hour as a clearing price. This would be the price that all the consumers would pay for the electricity and all the generators that are operating. So this would be these generators would receive as compensation, and this part of the supply curve, these power plants would not be operating, and these consumers here that bid too low, they would not get to consume because the price was higher than their willingness to pay. This basic concept basically follows Economics 101. So very briefly, for those who haven't done any economics courses so far, so the basic principle of the supply and the demand curves is that you have changing willingness to pay to consume a good. So here there's a demand curve for apples. So maybe the first apple is highly valuable for you, 1 apple for your break. But then as the supply or as your consumption of apples increases, at some point you don't really know what to do with them anymore. You maybe want to do apple pie or apple cider, but then your willingness to pay is not very high for the apples because you don't have a strong preference, for example, for making the cider. You would do it if you can get the apples reasonably cheap. And also on the supply curve, you have similar principle that maybe producing the first few units is relatively cheap of anything, of something. Cost of producing something, maybe because the first few units of your resource that you're using are quite cheap. But then at some point you need to go to other providers of this resource of this material that you're using, and you have to pay a higher price. So it's the same as in the power system. The first few units of electricity provision may be cheap. You have some low marginal cost generators, but at some point, if your demand gets very high, you might have to pay for expensive gas turbines. And then you basically put these two curves together, look for the intersection point, and from that you can get two main values, in equilibrium, the market clearing volume. So this is the kind of volume where you have enough consumers that are willing to pay the price, and that is matched with the same amount of producers willing to receive that amount of compensation. And that would then give you the market clearing price. So this is exactly what is applied to the power system, applied in this merit order, even though it's simplified here by neglecting any kind of willingness to pay for the consumers and just focusing on the demand side. How do we determine this supply curve or this supply curve? Well, we have to calculate the short-term marginal generation cost. Short-term because it's marginal, it's a generation cost that doesn't consider any of the investment costs of the unit. So in the long term, your marginal generation cost is maybe a bit higher because you need to finance your investments. But the short-term marginal generation cost would basically just consist of your fuel cost. Could be zero fuel costs in the case of wind and solar. Your operational dependent operation and maintenance costs, so your VOM, so variable operation and maintenance costs. So kind of a euro per megawatt hour of electricity produced cost. And potentially the cost of CO2 emission certificates that you need to buy at a certain price of euros per ton CO2. So you need to somewhat calculate, given the specific emissions of the fuel that you use and the efficiency of the power plant, the conversion efficiency of the power plant, to calculate kind of a euros per megawatt hour of electricity produced for the CO2 emission certificates. So that's basically what these short-term generation costs are. In the following, we will just use OS as a symbol for that. And it's really kind of fuel cost, variable operation and maintenance cost, and CO2 emission certificates brought to a euro per megawatt hour electricity price by using the conversion efficiencies and specific emissions. If you want, you can check the units. Check out the units that I did, prepared everything correctly, that everything here in this formula ends up in a euro per megawatt hour electricity value. And this example, I didn't want to do that all the way together with you, but we'll do the first case. And for that, I'll briefly switch to the iPad. So it's a very simplified case of a merit order. Here. So what we have 4 different types of power plants. We have the different capacities given. We have a fuel price, an efficiency, a variable operation maintenance cost, and the specific emissions. So these are just the input values that were on the previous slide. And we want to assume here now, or build a merit order for a 30 gigawatts demand. And I'll try to squeeze that in here so that we have simultaneous access to the values and the answer. So in the merit order, we would first of all put the 30 gigawatts of load at 30. So we maybe have 20 and 10 and 0 here. This would be gigawatts on this axis, and the price in euros per megawatt hour here. And now we would basically calculate the first case where we don't have any CO2 pricing, so we don't need to worry about the emissions at all. And we could now calculate the short-term marginal generation cost. For the first one here, we would have 4.5 euros per megawatt hour. So if we divide that by the efficiency, we would get 12 euros per megawatt hour electricity, already including also the variable operation maintenance cost. We would do the same for the hard coal, 11 by 0. Divided by 0.45 plus the 1 euro per megawatt hour electric. And we would get these different values. So what we need to construct the merit order is basically these short-term marginal generation costs of the different fuel types and the available capacity. And basically now go from the cheapest to the most expensive one. I think this one was on position 1. This one is in fact slightly higher if I consider the decimal points. And then we have at the third position this one, the fourth position this one. We have 5 gigawatts of the nuclear. Then we have, oh, actually, let me do that a bit better. So we would have at a cost of 12, we would have the nuclear. Then we would have at a cost of a little higher than 12, we would have the lignite. And then on third position, we would have 10 gigawatts of hard coal at a cost of 25. And then at a cost of 87 and 20 gigawatts, we have the CCGT gas. So here we jump now to 87 and pretty far down up to 45, we would have the gas. Our market clearing price would now be just the intersection point here, 87 euros per megawatt hour at 30 gigawatts of demand. And I would say the two other cases are something that you can do at home if you want, and I will bring the solution next time for you to check whether you did that correctly. Any questions on that? Okay, so if you've done any of the kind of energy economics or energy systems courses, this shouldn't have been new, but just to bring everyone to the same level. Okay, so what we did here implicitly by, sorting and looking for the cheapest, oh, that did not work yet. So what we did here implicitly is basically some optimization. We wanted to look for the lowest cost to provide the electricity demand of X gigawatts of X gigawatts. under the constraint that we actually fulfill this demand. And also, and another implicit constraint we did was that all the power plants remain within their rated capacity. So this is basically an optimization problem that we have already solved. And that was easy enough to do by enumeration, well, by just simply sorting. But if we wanted to formalize that into an optimization problem, it would look something like this. In red, you can see so-called decision variables. So these are decisions like which power plants operate at what rate at a given point in time. And everything that is in blue here are the input parameters. For example, the short-term marginal generation cost, the demand level, and the capacities of the generators. And we have one so-called objective to minimize the sum of generation costs and subject to some so-called constraints, which can be inequality or equality constraints. An example for the equality constraint would be that the sum of our generation has to match exactly the demand. And inequality constraints would be here, for example, well, our generation should be non-negative, bigger than 0, and less than each power plant should produce less than its capacity. And this is the optimization problem that we've solved so far. There's a few complications that we can add to that, but we'll get to that in a moment. So just in general, you have for every optimization problem the goal to find the best possible decision within given limits. What makes the best possible decision is typically specified with an objective, the goal, a function that you want to minimize. For example, minimizing costs, emissions, travel time, or maximizing profits and speed. You have the decision variables, the unknowns, the choices or the levers that you don't know yet that you want to find out. For example, how many pizzas you want to make or how far you want to cycle every day, subject to some constraints. The rules that you want to obey, for example, how many times a week you want to cycle, you must cycle to the office or something like that. It could be budget caps, maximum load on a bridge, or emission reduction targets. And then equality constraints could be these, are typically something like supply equals demand or inflow equals outflow. So we can do this simple example here. Another small optimization model that we can solve graphically. And here we have a demand of 500 megawatts and 2 power plants. We have one unit that is a bit cheaper with a cost of 3 euros per megawatt hour and a minimum output of 50 megawatts and a maximum output of 300 megawatts. And unit 2 is a more expensive gas-fired plant with a cost of 4 euros per megawatt hour, a minimum output of 100 and a maximum output of 400 megawatts. And what we want to find out is what is the dispatch of each of the units so that costs are minimized. What are the decision variables here? Well, the decision variables are the dispatch of the first unit and the dispatch of the second unit. We could say x1 and x2. What do we want to minimize? We want to minimize the cost. So 3 euros per megawatt hour for every unit of x1, 4 euros per megawatt hour for every unit of x2. And as constraint, we have the energy balance. Yeah, the sum of x1 and x2 has to equal the 500 megawatt of demand. And then we have the dispatch limits, which in this case are constrained both from the top and the bottom. And I should have stayed on the iPad because we can solve this graphically on the next slide. Where I now have this, so it's simple so that we can actually calculate that on a 2D graph. On x1, we have the dispatch of power plant 1. We have on the y-axis, we have the dispatch of power plant 2. And what we have as constraints, well, first of all, my X1 needs to be producing more than 50. So all that is excluded. And it can only produce less than 300. Yeah, so everything here is also excluded. My unit 2 can produce anywhere between 100. So this is also excluded, this combination. And it has to produce less than 400. So all this is also excluded. This gives me, first of all, a feasible range like this one here. But we have another constraint that we didn't consider yet. We have the case that the sum of x1 and x2 has to be equal to 500. So either we go everything with x2 and 0 with x1, or we supply everything with x1 and nothing with x2. And by that, we actually exclude also these combinations here because they in total do not add up to 500. So actually, the only things that are solutions that are feasible are on this line. Where on this line? Well, our objective is 3x plus 4x2. So that's something that looks like, so that has slope that looks a bit like this. Oh. So like this. So this is the kind of direction of optimization. We have so we have a 3-to-4 ratio of the cost of x1 to x2. And if we find kind of along this direction, the lowest solution, it's in this corner that x1 produces 300 and x2 would produce 200, the rest. So, and if we plug that into the optimization function, we would get a total cost of 1,700 euros. We can also quickly try to choose another solution, for example, using just 100 of, so this one, 100 of x1 and 400 of x2, which would give us a higher cost of 1,900 euros in total. So this is in principle how optimization problems are solved. In reality, you don't do this graphically. It can only be really done with two decision variables in a problem. But there's specialized software that can do that algorithmically for large problems. Good. So this is also the reason why we talk about optimization when we everything we've done so far, we could have done by hand. And the answer is that in reality, you just have a lot more degrees of freedom, so-called, or the decision variables, not only the dispatch of the power plants, but also operation of storage units across different time horizons. You can make decisions about the curtailment of the renewables, and there's also implicit decisions about the cross-border flows between market zones. So once we not only look at Germany, but also at other surrounding countries in Europe. And we also have a couple more physical constraints in addition to meeting just the energy demand at every point in time and every location and not exceeding the generators. We also have to deal with the kind of filling levels of the energy storage, and we have to keep the grid components, the transmission lines, within their limits so that they are not overloaded. So you can imagine if once we have a system where we have hundreds or thousands of nodes and thousands of time steps, so one time step for every hour in a year, these models become quite complex, and especially complex once you kind of go beyond just the electricity sector, but have more and more components like electric vehicles, heat pumps, and so on entering this system as consumers. Where then, especially this assumption we made initially of a vertical demand curve definitely does not hold anymore, and we have a lot more interaction on the demand side. So how do we make this model now more complicated, factoring in these different aspects mentioned on the previous slide? So let's go back to the one problem formulation that we had. Yeah, we have basically only a generator-focused optimization problem, minimizing the operational cost, keeping the generators within their limit and meeting the demand. And now we can add basically indices. We can add a spatial component I. That could be a market zone or a node in a transmission system. And now we get one new decision variable for each transmission line or interconnector between the market zones, which leaves the model the decision to decide how much flow you have from one region to the other. Within technical boundaries, we have new constraints, the Kirchhoff voltage law and the Kirchhoff current law. And the Kirchhoff current law is not really a new constraint here, it's just an extension of the energy balance, where we basically use the incidence matrix here to build an energy balance of the local generation, the local demand, and the kind of difference of incoming minus outgoing flows. Everything else basically stays the same, and with the addition that the absolute flows, so absolute because the flows could in principle go in either direction, also have to stay within a limit, very similar to the generators. The new parameters, the new input coefficients that go into this model are the cycle matrix, the incidence matrix K, and the line resistances XL, the flow capacity, the transmission line capacity, and a few things just have additional indices. So we have now a demand for each of the different regions. What we can do additionally is we can add a temporal component. So now we get an additional time index T for all of the decision variables, which just means we have dispatch decisions for every multiple points in time. And we can also get new parameters here, for example, this G hat, which would just represent the capacity factor of renewables that can vary over time. Or you could also have periods where a conventional power plant has an outage, and then for that period of the outage, you would have a factor on the nominal capacity of 0. This problem per se is not really more complicated because it's separable, because there's no connection between the time steps, and that is because we didn't add any storage units here, which would make just temporal arbitrage between charging and buying when the prices are low and discharging and selling when the prices are high, subject to some physical constraints that we discussed last week in the lecture. So here we have limits on the discharging capacity decisions, the charging capacity decisions, and there's also a variable that for the state of charge that also has to stay within the storage unit's energy capacity. the point where we get interconnections between the different time steps is through these storage consistency equations that we discussed last time, where we take the state of charge of the previous, the state of charge of the current period is determined by the state of charge of the previous period, plus its charging minus its discharging, considering all the different efficiencies from charging, discharging, and self-discharge. So in this way, we get a model that is not separable anymore because we want to optimize what is the best decision for the given storage capacities to operate over a longer time horizon. There's one more thing that we didn't talk about, or one component that I didn't introduce at the beginning of optimization problems, and these are shadow prices, or they're also called dual variables or KKT multipliers, Karush-Kuhn-Tucker multipliers. And I can refer you to textbooks for the theory behind them. I will just give you the interpretation of these values. So these are values that you can get out of software, out of solvers that solve these optimization problems. And these shadow prices are associated, with the constraints, and they measure how a marginal change, measure the marginal change in the objective value that is obtained by relaxing a particular constraint by a small amount. So for example, this mu s over bar on this constraint of the capacity limit of the generators would tell you how much cheaper the system would get if you had one more unit of that particular power plant. A very classical interpretation of these shadow prices is for the energy balance constraints, where the dual variable would really correspond to the market clearing price in the supply and demand curve that we looked at earlier, where it tells you the marginal cost of the marginal generator or the cost of consuming one additional unit of power. Yeah? So the unit of this shadow price will always be the unit of the objective function, so euros, divided by the unit of the constraint. So it could be euros per megawatt hour. There's also things you can imagine here that are often interpreted are CO2 constraints. So if you have a system where you have a limit on the CO2 emissions, there's a shadow price that tells you a value, a euro per ton value, because your constraint is in how many tons can you emit. That would tell you what the corresponding CO2 price would be that leads to this level of emission reductions. How do we get these values if we are not calculating by hand? So two main outputs that we get out of them, the so-called primal variables, so everything that is in red in the constraints, so the generator dispatch, the flow. This is something that we want to find out, and also the shadow prices might give us some useful information about our system. So there are these algorithms. There's the software that allows you to solve larger optimization problems. Some of them are open source and freely available, like HICE, SKIP, or CBC. And there are others that are commercial. They often come with free academic licenses, and they're just significantly more performant. So examples here would be Gurobi, Cplex, copt, or Express. And these are the tools that when we do research in our group, for simple things, we could still use the open source solvers, but then for the more complicated high performance computing models, we would have to resort to other commercial solvers. Conceptually, all of these yeah, all of this software uses currently two main algorithms, so-called simplex algorithm and the interior point algorithm. This is not a course about how these algorithms work, but I've brought one slide that conceptually explains how these work. In principle, they do what we did for the simple model graphically, and we can access these solvers then often through Python with packages like Pyomo, Pulp, and LinoPy, which we are going to look at next week. And in the simplex algorithm, the idea here is that you have your feasible space. So each of these kind of faces here would represent one of the constraints of the model. And we know from theory that the optimal solution would be on one of the edges of this space. And this algorithm works by kind of starting at one of the edges of, or one of the corners of this feasible space, and then traversing along this space for lower cost solutions. And repeat that basically until the optimum is found. And the other algorithm follows a bit of a different approach, where you just pick any feasible point as a starting point that is inside this space, and then you basically do a gradient descent in varying step size towards the corners of the feasible space, which is where you know your solution would be. And you stop this algorithm to kind of overshoot into the infeasible space, so space where you violate some of the constraints with so-called barrier terms, where you penalize solutions that come close to these constraints. And generally, I mean, both algorithms have been around for a long time. They're now there's one third category coming in now, which uses more of graphical processing units, but we'll see how performant they are. But for these kind of large scale continental scale energy system models, we want to kind of optimize the generation, storage, and the grids of a European system. We would generally use the interior point, or also called barrier method, as a solver method. And that is conceptually what all of these solvers do in the back end. What you'll be dealing with is basically just the interface to the solvers, and accept that they will do a correct job and find you the optimal solution to your model. So that actually already concludes today's sessions. I'll just leave with an outlook on what comes next week. So next week, we're actually going to look into LinoPy and how we can formulate optimization problems in LinoPy. LinoPy is just kind of one of the tools that you can use for that purpose. There's also a variant in the course website for Pyomo, which is another common framework for formulating and solving optimization problems in Python. And then the second block would be just the consultation hour for the second assignment. With that, I will conclude for today, and hope you have a nice evening.